Yes, this is the video for section 2.8, the derivative as a function. Okay, and in this video, these are our objectives. Okay, we find the derivative as a function. That is from, we're going to get the idea from section 2.7, where we find the derivative of a function. So as a function, meaning that, remember, when we find derivative, we always get a number, which is the slope of the tangent. And so here what we're going to do is that we're going to express it in terms of x instead of a. Okay, that's the only difference. And then we'll determine the relationship between when we say the function is differentiable at the point or it's also continuous at the point. There's a theorem, and then we'll look at whether that theorem holds for every situation. And then we have higher order derivatives of a function. Okay, so these are our objectives for this video. Now, from 2.7, section 2.7, you will notice that this is what we found. That is finding the derivative of a function at a certain point, okay, which is a, and that is given by this. So we are using the definition 4, okay, as we move forward from here. But all we need to do is that if you have the curve, all right, you pick the point A here. This point A over there, this will be different. So you see that the slope of the tangent is varying along the curve. So it is important to have a function that is finding the slope of the function, the curve in terms of x, so that when you know x on the curve, you'll be able to find the slope of the tangent easily. And so if you replace the a in this one with the word x, and that becomes that. Okay, so you have the slope of the curve, all right, which is the derivative of the curve. Okay, the derivative of the curve function is so f prime equal to the limit as h goes to infinity, goes to 0 of this expression. Okay, so we're going to apply this to a problem here, right, using that definition. Let me change my pen color. All right, so we have this. We're going to express that. Okay, so f prime, okay, of x is given by the limit h goes to 0 of what? F of x plus h instead of a plus h, and then f of x divided by what? Divided by h. Okay, so by my f of x is what? X cubed. So that means that I have to find the limit h goes to 0 of x plus h, you cube that, minus f of x, which is x cubed. Then, sorry, this is 3. And then what? We simplify that expression, h. Okay, so this is equal to the limit h goes to 0. And if you have x cubed, you expand this, you have what? X cubed plus 3x squared h plus 3x h squared, then plus h cubed, then minus x cubed, divided by what? Divided by h. And of course, this term will cancel out. And so you have the limit h goes to 0 of 3x squared h plus 3x h squared plus h cubed divided by what? Divided by h. And so if you divide each of the term by h, we have what? The limit h goes to 0. Okay, h goes to 0 of what? 3x squared plus 3xh plus h what? Squared. Now, if h goes to 0, then this is equal to what? 3x squared plus 3x times 0 plus what? 0 squared, which is basically what? 3x squared. So now you see that the f prime of what? Of the function is what? 3x squared. I know some of you are thinking of, oh, this is, why don't you use a rule? Well, we'll get to that in chapter 3. But right now we're using limits throughout, okay? So if I have, this is actually the slope. This is the slope, basically the slope of what? The tangent, okay, line at, not at a point, but at what? Any point. At any point on the curve. So that at any point. So if I know x is 1, then I can find the slope. If x is 0, I can find the slope. If x is what? 3, I can find the slope. If x is -1, I can find the slope. I just have to do what? -1 for x in this expression right here. Okay, in this expression. Okay, so now, sometimes if you have the graph of f, you want to know the graph, want to get the graph of the f prime. Now, because we see that the f prime or the slope is not a function. Okay, it is a function. Now, if it's a function, then we can find the what? It has a graph. Okay, now this is the guidelines. This is not in the book, but from my experience, if you want to get the graph of the f prime, okay, the graph of graphing derivative function given the graph of f. This is the procedure, because we are taking the slope around the curve f, or y equal to f of x. Okay, if the slope of the tangent is positive, so it means that the graph of the f prime, okay, here we are talking about a graph of what? F prime will lie above what? The x-axis. If it is negative, it lies what? Below x-axis. It is negative. And then if it is 0, remember, if you have a curve like this and it is 0, all right? So it means that it is horizontal. What it means that it crosses the x-axis at that point. Okay, so here is one example. I've been given the graph of what? F of x, which is this one. Okay, now how do I get the graph of what? The f prime from this, the derivative? Well, I'm taking slopes along this curve, right? So if I draw a tangent to this, okay, you see that this is what? Positive. Now here, it is what? The slope is what? 0. If I take any slope here, it is positive. Here it is what? The slope is what? Is 0, or the tangent to that is 0. Over here, okay, it is what? Negative. Now over there, it is what? It is 0 again. And then like this, it is what? It is positive. So what is happening is that every point to the left up towards 0, okay, since it's positive, the graph is going to lie above, sorry, it's negative, it's going to lie below the what? X-axis. So if I'm drawing it, it's going to come something like that. Okay. Now, if it is 0, what is this? At maybe 1.5, at this point, okay, at this point, the graph is going to cross that. Okay, it's going to cross that point. And then at this point too, it's going to cross it. At that point, it's going to cross the x-axis and it's going to lie above. So here it will lie below, it will lie above. So we have this together, okay? When I have this point, since this is what? Remember, this is what? This slope of the tangent is negative. So it lies below. So it's going to go like this and come all the way, okay? At this point, when it is 0, it is going to cross the x-axis at this point. Now, this is what? 0. It is 0. It crosses at what? At that point. And then here it is 0. It crosses at that point. Now, look at the slope. This is negative. So it lies below x-axis. That's why it's coming that way. And then once it crosses, right, the slope changes to what? Positive. That's why it lies what? Above. So it's going to go above. All right. Then we know that it comes back to cross it at this point. So definitely it's not going to go up. It will turn somewhere and come and what? Cross the x-axis again. Because from this everywhere here, it is what? Positive. The slope of the tangent line is positive. That's why it lies above the what? X-axis. And then after that, the slope changes to what? Negative. So it lies below, and then also comes to cross it again at what? C prime. Okay, we label this ABC. So what is happening is that it lies below x-axis, above x-axis, then below x-axis, and then above, because after this the slope is positive. And so this is the slope of this is a curve of what the y equal to what f prime of what of x. Okay, so we'll do another example in class, so maybe you understand that better. Okay, now there's other notations. We will call this what Leibniz what, I hope I pronounce that word, sorry, Leibniz what, notation. Okay, now if you have seen the dy, we say dy dx. So basically the f prime is also, since we have y is equal to f of x, f prime is the same as y prime, which is the same as what dy over what dx, like that. Okay, that is differentiate y with respect to what x. Now it's f of x. I can also say that I'm differentiating. So if you write this dx, okay, meaning what? Differentiate, okay, differentiate f with respect to x. Okay, WRT means that with respect to what? X, with respect to. All right, now that's the same as this. Okay, what I have here is my differentiate this with respect to f. That's the same thing. Now sometimes we use d. Okay, we use just d, meaning that is an operator. Okay, that's an operator. And so if I put x there, it means that I'm differentiating the function with respect to x. Okay, so these are all notations. And then sometimes after differentiating, we have the, for example, we have f of x is equal to the 3x that we got. Okay, now if I want to evaluate this at x equals to 2, I'll write this as what? Dy dx, because this is the same as what? Y prime. So dy dx, and I put a bar and say that x is equal to say 2. So if I want to evaluate that, then this would be what? 3x times what? 2 squared, which is 4 times that. That is what? That is 12. Okay, so this is what this notation here means. It means that we are evaluating the derivative at what? A certain value of x. Okay, so we have that. Okay, so in the Leibniz, as I've explained, that is what it is. Okay, now we are evaluating what? The derivative at x equal to a. So x equal to 1, x equal to 2, whatever value of x you use. Okay, now when it comes to continuity and differentiability, so a function is, say, we call it differentiable if f prime what exists. Okay, and then it is differentiable on an open intervals. Either you have this interval or a toward positive infinity or negative infinity to a, or negative infinity to positive infinity, if it is differentiable at every number in the interval. Okay, so this is what we call the differentiability and what? The continuity. There's a theorem, okay, and then remember when you say a function is continuous, right? We said that the f of a must equal to the limit x goes to a of what? F of what? F of x. Okay, if this limit exists and this exists, then they are equal, then we say that the function is what? Continuous. So we're going to combine continuity and then what? Differentiability in the following what? Theory. Okay, so there's a theorem 4 in the test which says that if f is differentiable at a certain point a, then it is continuous. Okay, that is, if you have the limit as a goes to what? S goes to a of f of s equal to f of a, then we say that this function is what? Differentiable at a. And if it's differentiable at a, then it is continuous. So the question is the converse of this theorem true? What do we mean by that? That is, if the function f is continuous at a, does it mean that it is what? Differentiable at a? Okay, to answer this question, we'll look at a specific example, which we'll call a counterexample, and see what in the next slide. Okay, so here's my function f of x, which is which is what absolute value. Okay, now absolute value of what x, I want to define that, making sure that we remember. Now absolute value of x is equal to this. It's a piecewise function. Is equal to x if x is greater than greater than or equal to what, 0, and it is what, negative x if what, x is less than what, 0. If it's negative, then we have negative x. So that when you plug in something like negative what, 2, absolute value of negative, you have a minus of what, negative 2. That is what, that's positive. All right. So that's the graph here. But the question is that we want to say that is it differentiable at 0? That means that you see that curve, you know that it is continuous, but is it differentiable at this point? Okay. So we're going to use a definition and then find the what, the limit to that. So now let us find the f prime at what, of x. So let's find f prime of x. Okay, which is the limit h goes towards 0 of what, f of x plus h minus f of x, all divided by what, h. Now let's do some work of algebra here. So f of x plus h means that I have to find absolute value of x plus what, h minus absolute value of what, x divided by what, h. Now we want to find, okay, the x is equal to, so when x equal to 0, then f prime at 0, what is that? It is this limit, okay, h goes to 0 of what, absolute value of 0 plus what, h minus absolute value of 0 over what, over h. Now this simplify into the limit h goes to 0 of what, absolute value of h divided by what, h. Now if I use the definition here, what is absolute value of h? This is equal to what, h if h is positive. Okay, h is greater than equal to 0, or it is what, minus h if h is what, negative. Okay, because in this case it could be what, any of such. So then this gives me two outcomes. That is the f prime of 0, that is if h is positive, right? If h is positive, then this derivative is actually the limit h goes to 0. This will be h over what, h, which is equal to what, 1, because the limit of a constant is what, constant. Now if h is what, negative, then f prime of what, f prime at 0 is going to be the limit h goes to 0 of what, minus h over what, h, and that gives me negative 1. Now you see that this is what, that is not, the limit does not exist. So you cannot say that this limit, so we can say that the limit h goes to 0 of what, okay, or just simply you can say that f prime of 0 does not what, exist, because 1 is not equal to negative 1. Therefore, what can we say? We say that the function is continuous at 0, but not differentiable at what, 0. So our question is answered. And so going to the graph, it is continuous. When you have a corner like that, we're going to generalize. You have a corner like that, you will say that it is what? It is not differentiable, but it is what? It is continuous. Okay. So generally speaking, okay, the converse of the theorem is false. That is, there are functions that are continuous but not differentiable at certain points. So a function is not differentiable at a number if the graph of f has the following. It has a corner, it has a jump, or it has a vertical or tangent, as we see in the following graphs. So as you can see here at A, what's the tangent to that? It doesn't make sense. So we say that the function is not differentiable at A. In the second graph, is a corner, there's a jump, okay? right? We say that it is what? It is discontinuous, right? It is discontinuous and it's not differential because the limit, if you take the limit as it goes toward positive, you have this value of what? This value of y, and then x goes toward a negative, have this value of what? So let's say this is b and this is what c. Of course, b is not equal to what? C, and therefore we say that the limit, okay, the f prime of a does not what? Exist, just like we do. So the third one is that if you have this, that the tangent, the vertical tangent like that, there's the slope of a tangent line. It's just undefined. So basically, we say that this is what? The function is not differentiable at what? At A. Yet it is continuous in this, in the C. It is discontinuous there. It is continuous at A, but it's differentiable at all the A's in the following, those what? This graph. So 3 ways for f not to be differentiable at what? At A. Okay. Now, we have higher order, derivatives. So we can find the first order, which is just f prime. Okay. And then the second order, which is f prime prime, meaning that you differentiate the first derivative. Okay. Which is kind of funny to say. It is the, you find the rate of change of rate of change. Okay, because the f prime is a rate of change. So if you differentiate it again, you'll find the rate of change of rate of change. All right, and if you differentiate the third time, you'll find the rate of change of the rate of change. Yeah, you get it, the drill. But in using Leibniz notation, okay, if I differentiate, you have my dy dx. If I differentiate again, this is how we write it. Okay, this is a second derivative. Please, this is not the same as what? Dy over dx all squared. Please, don't think of this that way. Okay, this is an operator. This means that differentiate the first derivative again. All right, so that's a second order. Or you can say that this is the f dy ds. Okay, you can say that dy ds is what? The first order. Then d squared y over dx squared is what? Second order. Okay. Now, in real life, okay, if you have an object moving in a straight line, okay, so we call the object, this is a displacement or the position function, or we call it a displacement. That's another way to call that. Okay, function. Now, as you are driving, you set off your car, you're moving, the car is moving, and so what is changing? The displacement is changing, and that is what we call the velocity or the instantaneous velocity. And to find that, you differentiate that, you differentiate your displacement function to get the rate. That displacement is all the position is changing, which is velocity. And then as you are going, stepping on the gas, guess what? Velocity is also changing. And that is what we call the acceleration. And then when acceleration, you are coming to a stop, it's also changing. We call it a jerk. Okay, if somebody is a jerk, sorry, that is what it means. Because if you, those of you who know how to drive the manual, the stick shift cars, see, if you are changing, when you shift the gears, the car kind of jerks. So that tells you there's a momentary change in acceleration. That's what the car kind of jerks a little bit. And that's what we call jerk, okay? So if you don't know anything, somebody says a jerk, that means he's changing acceleration. All right, now these are the notations. So if I have the displacement or the position function, v of t is a first derivative of the displacement, which is that, or ds over dt. Acceleration is what? Dv dt. So basically the acceleration is a second order differentiation of the displacement or the position function, which is d squared s divided by dt squared. And then the jerk is what? The third, okay, the third order of what? Of the position function. All right, so we have velocity, so the displacement, velocity, acceleration, and jerk. All right. So generally, if you have the fourth order, and also we're going to use this notation for that. So my first order f prime, we know this is the same as y prime. My f prime prime of x is what? Y prime prime. That's the same as what? D squared y over dx squared. If I have y to the fourth, okay, to the third, we'll just use f prime prime prime. Okay, y prime 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 or f prime 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 prime, okay, will be what? The d cube y over dx cube. But after that, we'll use this notation. If I write this, it means I'm differentiating the fourth time, which is d to the fourth y over dx to the fourth. Okay, so if you write this to the parentheses, that will be d to the fifth y over dx to the fifth. Okay, so these are the notations, means that you have to differentiate the function to the third. All right, so I'm going to use one example, okay, that we will find just the second derivative. We can find a third and then a fourth, and that will be the end of this section. All right, now what's the definition? This is what f a is what? This is my f of x. Is the limit h goes to what? 0 of what? F of what? X plus h minus f of x divided by what? H. So then this is equal to the limit h goes to 0, and you have 2x plus h all squared minus 2x squared, sorry, x cubed, sorry. Okay, all divided by what? Divided by h. So then this is equal to the limit, okay, h goes to 0, and then 2 out, we have 8 cubed plus 3x squared h plus 3x h squared plus what? H cubed, okay, the minus 2x cubed, all divided by what? Divided by h. Now let us do some algebra there. The limit h goes to 0. Now distribute the 2 over, you have what? 2x cubed plus 6x squared h plus 6x h squared, then plus what? 2h what? Cubed minus 2x cubed. Now guess what? That will cancel out. By the way, everything divided by what? Divided by h. Okay. Now if h divide each of the terms, then we have what? The limits h goes to 0. They have what? 6x squared plus 6xh plus what? 2h squared. Now as h goes to 0, then you have what? Just 6x squared plus what? Plus 0 plus 0. So that is equal to 6x squared for the derivative, which is f prime of f prime. Now, if I want to find the second derivative, okay, which will be the limit, okay, h goes to 0 of f prime of x plus h, using the definition, minus f prime of x divided by what? Divided by h. Okay. So let me go so that I get more space. This will be the limit. h goes towards 0. What is my f prime of x? It was 6x squared. So this will be what? 6x plus h all squared minus 6x squared divided by what? Divided by h. So I'm differentiating the what? F prime. Okay, that's why it gives me f prime prime. So this is the limit. h goes to 0. Then let's expand x plus h all squared. So 6 is out. That gives me x squared plus 2xh plus what? H squared minus 6x squared divided by what? H. And that gives me h goes towards 0. And if you expand, distribute 6 or take 6 multipliers every time, that you give what? 6x squared plus 12xh plus 6h squared minus 6x squared divided by what? H. Now this cancels out, and then if h cancels one of this and cancels one of that, cancels the h there. So we have what? We have the limits. H goes to 0 of what? 12x plus 6 what? H. Now if h goes to 0, then have what? 12x plus what? 0, which will give me 12x. Okay, so first derivative, second derivative, we can go third derivative, that is differentiating what? The 12x, the second, again, which will the same as differentiating the third, the original, 3 times. Okay, so that is the end of this section, and the next one will follow soon. Thank you.